2 units in this quarter. Unit 4 is the longer one and has, I don't want to say the most complicated math, but it has more math. Okay. So I'm recording at this point. Yep, I'm recording at this point. Let's go ahead and get started. I am going to go over the bell work so that everybody has the answers and how to get them. This is from a newer exam, so it's important to see how the questions are being asked when they don't give you the data booklet. They tell you H2PO2 minus is a strong reducing agent. What does that mean? It reduces other things. That's what a reducing agent does. It makes other things be reduced, which means it's going to be oxidized, generally speaking. It can be used to reduce metal cations without the need for electrolysis. That means no battery needed. It'll happen itself. And so they give you equation 1. How do I know this is a half reaction before I even read forward? Because I see the E minus. And half reactions are provided to you when they're provided to you as reductions. But if it's actually an oxidation, you're going to have to know to flip it later on. And then they give you the number. This is the reduction voltage. So then part 2 here. The Cr3 plus Cr half cell has a standard electropotential of negative 0.74. But they don't give you the half equation for it. You will have to come up with it yourself. But it's not a difficult one to come up with because you would just need to know where to place the electrons when it comes to the time, if it came to the time, which it technically doesn't. And then they tell you a full cell consists of this and this, and they ask you to calculate the cell potential. I taught you a formula last class, and I gave you a quick way to remember it. To find the E of a full cell, you could do the E of the reduction minus the E of the oxidation. E, read, ox, like that. The reduction minus the oxidation. And how would we figure out, well, what's the reduction and what's the oxidation? You have to look at these two numbers. And I mentioned that the more positive number would be reduced and the more negative number would be oxidized. Do you remember that? This is the key information you have to remember. The more positive E value will always be reduced, and the more negative E value will be oxidized. If you take out any information from that lesson, that's super important because that's how you're going to make all your decisions. If you don't remember that, you're not going to make the correct decision. And so these two values, neither of these are positive. So how would we make the decision? I mentioned you could make a little number line. Put the two numbers on a number line, right? So you'd have 0, negative 0.74, negative 1.57. The way to understand it is the more positive one would be going that way, right? And the more negative one would be going that way, right? This is more positive. This would be more negative. So using a number line, we can state that negative 1.57 is the more negative of the two numbers, which means it's the one that's going to be oxidized. And the negative 0.74 is the one that's more towards the positive, so that would be the one that's reduced. And that's the essential information that you need in order to solve this question. Because to do the math, it's going to be negative 0.74 minus negative 1.57. And which means it's negative 0.74 plus 1.57. And that's going to lead us to an answer of 0.83, which was worth 1 mark, if you got that. So check to see if you got that. That's worth 1 mark. It's literally just knowing which numbers to subtract. No. 1. Literally 1 mark because it's 1 subtraction that you're doing. Now, here's where a lot of times, not every single Cambridge exam, but many paper 4s, I would say half of paper 4s, just to give you a number. Half of paper 4s have a diagram on this topic. And those marks are easy as long as you remember all the things you need to incorporate. So this is the sheet. They're telling you it's the sheet. And they want you to construct the chromium half cell versus the sheet. So then you would have to start by writing yourself a little beaker. And then you would do what? I would do this, write a little B for the voltmeter. If you put the letter V, that's enough to say this is the measurement device that you're using to measure. And then, oops. And then we would need this wire to continue and go into here. We need a water level, and then you have this. What is this electrode made of? Chromium. How do we know that this electrode is made of chromium? So you can either write CR inside, or you can write an arrow to it and write CR, like an arrow pointing here, and then say that it's made of CR. Why do we know it's made of chromium and not platinum? Because they tell you here, this is the pure metal, which means you're in a metal ion, metal solution. If you've got the pure metal is the electrode because it's not dissolved in the solution. All right, so we're getting there. What else do we need to incorporate? This is called the salt bridge, and they do require you to label it. So label it the salt bridge. In the chromium solution, what else should be there? We've got the chromium electrode. What else should be there? Cr, 3+, and it should be aqueous. It should be aqueous. Over here on the sheet, what's coming in? What's the gas going in? H2. And what's in here? H+, the acid. So that's good. Now what do we need to include? We need our conditions. Our conditions are 1 atm, 298 Kelvin. Solutions are 1 mole dm minus 3. And then let me check to look at the mark scheme. They also want, what is the identity of this electrode? What is this? You have to write PT, or point an arrow to it and put PT. So then, where are the marks? They give you 9 things, and I'm going to read them out. Every 3 that you get a mark. So the first one was platinum, chromium as the electrode, and H+, or any strong acid. You could have done HCl, H2SO4, they accept it. So that would be 3 bullet points, that's 1 mark. The next is Cr3+, AQ, H2 gas, and a voltmeter. So that's a mark if you have all of that. And then the last one is the salt bridge is labeled. You have your conditions, and you have a liquid level would be the last marks. If you forget the liquid level, that actually knocks off a mark. So you have to include the liquid level. So this would be a completed voltaic cell. So we've labeled it. Now, how do we determine which is the positive electrode and the direction of electron flow? So what is the electric potential of the sheet? Even though they don't give you a data booklet, I would say you need to know it. That's why I had you highlight it. It should be 0 because everything's compared to the sheet. So you should know that this is 0. Yes? And the E of Cr3 plus to Cr, we had it on the other page. What was it? Because here it's negative 0.74. So which one is the positive electrode? Because in order to determine the positive electrode, you need the numbers to pick this up. The one that's more positive is the positive electrode. So the positive electrode is the sheet. So the signs would be plus, minus, like that. So far, are we good? Finally, the direction of electron flow should always be from anode to cathode, from what's being oxidized, from what's being reduced, from where the electrons are going from to where they're going to. So the direction of electron flow is like this. You can either write it like that with the E minus, going like this, or you could say from right to left. In this specific diagram, it's from right to left because of the way that we've drawn it. Does that make sense? All right, so that's 4 marks. The reason I'm going so slowly over this, and that's why we have a lab on it as well, is there a good chance this shows, even if it doesn't show up on your paper 4, could this also show up on your paper 5? To build this, yeah, it could show up on your lab analysis paper. So being able to construct these diagrams is extremely important that you know how to do, which is why we're going to continue reviewing them pretty much daily until you take the exam. Ready to continue? All right, this one is probably the trickiest question. I would say that this is the trickiest question here. And it's worth 1 mark on top of it. This is the trickiest question, it's worth 1 mark. But it's not impossible to do. If they say H2PO2 minus, which they give you an equation with H2PO2 minus in it, reduces nickel 2 plus to nickel. So they're telling me what happens, that this is being reduced. So if nickel is being reduced, that means that H2PO2 minus itself is being what? Oxidized, because there must always be 1 reduction and 1 oxidation. So that information is telling you kind of what's happening. So I would write out nickel 2 plus goes to nickel. Which side do the electrons have to be on? They have to be on the reactant side, because 2 plus and 2 minus will cancel out to become a charge of 0. And then, well, right now, what they're asking me to do is use this equation to put these 2 equations together. When they say ionic equation, they just want the full reaction. It's an ionic equation. It's called an ionic equation. Ionic equation, which I know was an issue last year in AS chemistry. All that means is that the spectator ions are not being shown. So you may want to write that on the side. That's why you see all these charges here, because there would be some kind of metal there, but it's just not being shown because it's not actually doing anything in the reaction. So in an ionic equation, spectators are not shown. They're existing somewhere in that solution. We're just not showing them to you. So that's an ionic equation. Also, you can remember you see ions in an ionic equation. And so how will we put these 2 equations together? We know this is reduced, and this is supposed to be oxidized, right? But this is a reduction right now. So what do we got to do to equation 1? We've actually got to reverse it, meaning we've got to make the reactants the products, and we've got to make the products the reactants, because this has to be oxidized. But what's being shown to you right now is a reduction. So we are going to rewrite this as H2PO2 minus plus 3OH minus goes to HPO32 minus plus 2H2O plus 2E minus. And that's the oxidized version of it, right? Where the electrons are coming out, not going in. Now to put the full equation together, what do? Cancel the electrons and smoosh everything else together on the same side. So this would be nickel 2 plus H2PO2 minus plus 3OH minus goes to nickel plus HPO32 minus plus 2 waters. And if you write 1 single charge missing or wrong, the whole thing is wrong, and this is worth a single mark. This is probably the trickiest question of this spell work, I would say. Well, some of you got it right on first attempt, so pat yourself on the back. You did. You got it right on first attempt. All right, so we are going to begin now the final lesson of the unit, so I do need your full attention. What we have to go over today is what happens if the concentrations are not 1 molarity. How does that affect the E values? And so we will be returning today to Le Chatelier's principle. I know everybody's favorite. And how does equilibrium come into play? We'll also be looking at delta G and how this integrates into delta G today. So this is the final lesson of the unit. Unit 3 part 5 is looking at non-standard concentrations and how everything interrelates into spontaneous and non-spontaneous reactions. So let's get to it. These are our objectives. We've got 3 of them to cover today. It's like a Goldilocks amount, not too few, not too many. So that communicates hopefully that the lesson's not crazy hard, but it's not the easiest because it's not a ton of objectives on the same day. So we are going to learn something called the Nernst equation today. And that is an equation that will need to be memorized. There will be 2 formulas today that you will need to memorize. So let's say what we have to do in our learning outcome. We need to predict qualitatively how the value of an electric potential varies with concentration of aqueous ions. So qualitatively means math or no math? What does qualitatively mean? No math. So this is going to be using Le Chatelier's principle. Which can be used to explain a great many things. Le Chatelier's principle. So we'll predict, using Le Chatelier's principle, how the value of an electric potential is going to change when we change the concentration of aqueous ions to be greater or less than 1 molarity, right? 1 molarity is the standard. That's why we have to memorize the standard. If it's different, we're going to have to know how that changes things. And then it says use the Nernst equation. And so the Nernst equation is this one. And I would say, although they give it to you on some tests, I would go ahead and memorize it. Use the Nernst equation. E equals E for a half cell plus 0.059 divided by Z plus log ox spread, actually. Oxidized species over reduced species. And this is going to predict quantitatively. So this is calculate. That means we're going to do the math. This is going to be your calculate questions. Quantitatively, how the value of electric potential changes when we change the concentrations of aqueous ions. And we'll be looking over how to use this formula today and what everything stands for. And then finally, we're going to have this fun little equation. This is new for 2022, but it's something that is definitely used in college level chemistry. Delta G's relationship to the electric potential value, which is delta G equals negative NEF. Before we get started, in the last lesson, we did learn an equation that you absolutely need to remember, and it's the one I wrote before, right? So what was our calculate equation for calculating E cells? You should have this with you as we go through today's lesson. You should also pick up your data booklet if you have the data booklet from last class. I did print out a data booklet for each of you. Well, or the 2 pages from the data booklet that just has the E values, but I've also printed out a full data booklet for you. You should either have the data booklet or the printout of the values so that you can refer back to them. I have them also on Schoology. I have the data booklet posted on Schoology for you, but usually if I'm just looking for it myself, I will go online and I'll go online and I'll just search up 9701 data booklet, and it's the first thing that pops up. So if you just want to know, you need the data booklet quickly, you can Google it. 9701 is our syllabus number, and then data booklet, you pull that up, and it'll say chemistry, first thing that pops up, and then the data booklet is there. If you search up 9701 data booklet, you can find it online at any time. You will need this today at some point for electric potential values. I'll keep this up for when we need it, but you should have your own for when you're doing the homework or the one referenced to pull to. So let's go ahead and get started. Okay. So first of all, the first standard was how do we look at E cells at non-standard concentration without numbers? I do need your attention. Oh yeah, you got it? Cool, awesome. When we discussed equilibrium, we saw that equilibrium was affected back in the first time we discussed equilibrium. We could look at changes in temperature, pressure, concentration, and looking at those changes would tell us whether the reaction shifted to the left or shifted to the right. So what's important here is to remember for E to be spontaneous, what sign does it need to be? For E. For E to be spontaneous, for a reaction to be spontaneous, what sign does it need to be? It needs to be positive, right? It has to be a positive value. If you don't have a positive value, that means that the reaction is not going to proceed in the way you think it is. It's actually going to proceed in the opposite direction. So a positive E value will tell you that the reaction is going to happen as is. And so we will be able to look at Le Chatelier's principle and state if we make more products, what would that happen? What would happen to the E-value? So if we make more products, what would happen to the E-value? If a reaction shifts to make more products, would the E-value increase or decrease? So if reaction shifts right, the E-value is going to increase, meaning it's going to be more positive, it's going to be more spontaneous, you're going to make more products, right? And if the reaction, according to Le Chatelier's principle, would shift to make reactants, what would happen to our E-value? So if the reaction shifts left, what would happen? So if reaction shifts left, if reaction shifts left, whatever factor we change shifts it to the left, the E-value would decrease. Either become less positive or even negative, as your reaction will shift to make more reactants. And so we're going to be analyzing, looking at Le Chatelier's principle, whether our E-values are going to increase or whether they're going to decrease. And this is literally just going to be looking at whether the reaction shifts to the left or shifts to the right. And so we have a couple of textbook questions. Here's a first example. You've got some zinc 2 plus, half reaction, plus E minus, that should say 2E minus, put the 2 there. Is zinc solid? Doesn't affect the answer, but just because. And we've got an E-value. Standard condition for the cell is 1 molarity. If the molarity of the zinc 2 plus ion was changed to 0.5, how would this affect the E-value? So this is supposed to be 1. What happens if this becomes 0.5 instead? That concentration would decrease, right? If the concentration on the reactant side decreases, what does Le Chatelier's principle say will happen? Whatever side we have too little of, it's going to make more of that, right? To restore equilibrium. So if the reactants are decreased, equilibrium will shift to the left, right? It will shift left to make more, to restore balance. Because the whole concept of Le Chatelier's principle, if there's too little of this, it's going to make more to restore the balance, right? So the reaction would shift, equilibrium would shift to make more reactant to restore the balance, which means what's going to be the effect on the E-value? If the reaction is going to make more reactants, what happens to this E-value? Does it increase or decrease? It decreases. Because remember that increase will be more positive E-value, decrease will be more negative E-value. That's the idea. So whichever direction the reaction's going is going to tell you what happens. And so what would be the effect on E? It will decrease. Or become more negative. Is another way to say that. Become more negative. Does that kind of make sense? I have too little reactants, so the reaction must shift to restore balance by adding more reactants. So whatever side you have too little of, you have to bring that up in Le Chatelier's principle. What about the second one? Second one's the opposite scenario. We are now increasing our molarity of zinc 2 plus. So what happens if you increase the molarity from 1 to 2? What happens according to Le Chatelier's principle? If I have too many reactants, in order to shift the balance, what has to happen? You have to make more products, right? If I have too many reactants, reaction shifts the opposite direction from where I have too much. And so I'm going to make more products if I increase the concentration. If I make more products, because equilibrium shifts to the right, what happens to the E-value? It increases. We don't know how much it increases by. This is not quantitative yet. We just know that it's going to go up, right? So it will increase. So this is yet another application of Le Chatelier's principle, or become more positive is another way to say it. It will increase or become more positive. And so that means that the value is going to change from negative 0.76. Quantitatively, we're going to have to figure out shortly, how does it change? What number does it change to? And that's why I said there's a formula for that you will need to know. And so will this affect spontaneity of a reaction if we change the E value? The answer is yeah, possibly it could. It could change a non-spontaneous reaction to a spontaneous reaction, or it could change a spontaneous overall reaction to a non-spontaneous reaction. So changing the concentrations will alter the spontaneity, especially if the E values are within 0.30 of like 0. So if your overall cell reaction is within 0.30 of 0, that means that it could flip with a change of concentration from spontaneous to non-spontaneous. So this is talking about when you have small differences in E values from your reduction and your oxidation. So not like if you were working with lithium and fluorine, but if you were working with things that had lower potential differences. So for differences less than 0.30 volts, we will have to use the math to figure it out, whether it flips to spontaneous or non-spontaneous, which we're going to see shortly. But let's take a couple extra looks at questions from the textbook. So check up 26. That means we're 26 exercises through this chapter is what that means. That's pretty far. That's how you know that you're in the final lesson of the chapter. CR207 2 minus plus 14 plus 6e minus goes to that. You've seen this equation before. It's one of the more complicated half the reactions, but I know we've seen this before in Bellwork. They tell us we have an E value of 1.33 volts. Suggest how the E value changes if everything is kept constant except for one thing. CR207 2 minus is increased in concentration. What would happen to the E value? CR207, you increase this, right? So put your arrow up here, meaning I have too much reactant versus product. So what does the reaction do? Makes more products. So what happens to the E value? Makes more products means increases. So it's going to be a bigger number than 1.33, right? Some bigger number than 1.33 volts. What about if H plus is decreased? Everything else is kept the same, but we take H plus and we have it in a less acidic solution. So a less strong acid, less acidic solution. What will we do? It goes this way, right? This goes down, that means reaction shifts to the left, so it goes down. So this means that it decreases E value. And can there be Cambridge questions that just ask you to analyze this? Absolutely, it's one of the standards. So yes, it could be, as long as you remember what's going on. These are not difficult marks to achieve. CR3 plus is increased. So CR3 plus is on the product side. If I increase my products, what does the reaction seek to do? To restore balance. Make more reactants, right? Which does what to the E value? Decreases the E value. Are we getting the idea of what to do here? So more products, more positive. PP, more products, more positive. More reactants, more negative is the idea. Products positive. Protons positive. Protons positive, products positive. So on and so forth. So, ready for the math? We're here. Time for the math. So that's qualitative. We did the first standard. The second standard is, well, how do we actually figure out what number it changes to? And so we use something called the Nernst equation. This is called the Nernst equation. You should write it down. I would memorize this. Even though in the 2022 standards, I do see that they say to use it, I would say that you should have this memorized. Let me double check the wording of the other standard. Understand. Yeah, this one you also have to have memorized. So E equals EO. This is the standard cell potential. And then this right here is non-standard, like at your altered at your altered concentration. And so you have 0.059 on the top, Z on the bottom. Z stands for the amount of moles of electrons transferred in the half reaction. So moles of electrons plus moles of electrons transferred in half reaction. And then log of your oxidized form versus your reduced form. So oxidized form of your half equation will be the one that has the more positive charge, and the reduced form will have the less positive charge. So for example, if I had Fe3 plus E minus goes to Fe2 plus, which of these two would be my oxidized form of iron? If I have concentrations of Fe3 plus aqueous and concentration of Fe2 plus aqueous, which one is my oxidized form? This is the oxidized form. The oxidized form is the one that has the more positive charge, right? And the reduced form, so just to point that out, the reduced form of whatever ion you're looking for is the one that has the less positive charge. So the oxidized form would be the one that has the more positive charge. I think I had mentioned to you all last year, I had a student that memorized oxidation, like they came up with this themselves as oxidation more positive. And that falls into play here. The oxidized form is the one that's more positive. One way to memorize oxidation and reduction. Oxidation more positive. What confuses everybody with redox is the sign. That's why we come up with these little acronyms to help us to remember what's going on. All right, so this is the equation. You're going to need this to solve questions. Notice there's a logarithm key there, so you're going to need a scientific calculator to solve questions. So we're about to get to the actual math. The math itself won't be entirely difficult. It's just whether or not you memorize the equation or not, if you're going to get the answers correct. Let's take a look at some questions. Yes. That's constant. The derivation of it would require a math course higher than this. But there is a derivation for it to change from standard to non-standard concentration. An electrochemical cell is constructed using two half cells. You've got SN4 plus to SN2 plus, Al plus 3 to Al. Can you tell if this is a Cambridge question? By the writing? Yes. Totally Cambridge. Paper 4. Paper 4. What's the material used for the electrode in each half cell? SN4 plus to SN2 plus. Right? Al3 plus to Al. Al. Good. 1 mark. If you can remember that. 1 mark. And how often does this mark seem to be showing up? To figure out the identities of the half cells? All the time. It's on a lot of tests. The cell is operated at standard temperature, right? That's what this is saying. This is standard temperature or room temperature conditions. And then they tell you that the Al plus 3 aluminum half cell has standard concentration being 1 molarity. And they tell you that the SN4 plus SN2 plus half cell does not have standard conditions, standard concentrations, right? These are not standard concentrations, not standard. And then they tell you to use the Nernst equation to calculate the potential of this half cell. So the Nernst equation to find the concentration of the half cell. Because this is a question that is before 2022, you need the data booklet in order to pick up the standard cell potential for SN4 plus to SN2 plus. So head to your data booklet and figure out what is the E cell for the standard cell for SN4 plus to SN2 plus. I'm going to go ahead and also look at the data booklet because I don't have all the standard cell potential. SN4 plus to SN2 plus. That's this one right here. SN4 plus to SN2 plus is positive 0.15. So we need that number. That specific number. I'm sorry, what? Okay, so the formula is E equals the standard E for the half cell plus 0.059 divided by Z, and then it's log of the oxidized form over the reduced form, which I just go oxred. That's how I remember it, because I don't want to write all those things. So far, so good? That's the formula. That's how I remember the formula, by the way. I don't write oxidized form over reduced form. I just write oxred, because I think that's less. Yes. You can scan, show, and go. So our E cell, we just picked up. The standard E cell for the tin was positive 0.15. Do you agree? So I'm going to plug that in here. Positive 0.15. 0.059 over Z. What is Z here? The amount of electrons transferred in this half reaction are how many? 2. And you look at the difference in the charges to figure that out, or you could look at the half reaction in the data booklet, it's 2. Right? SN4 plus 2E minus goes to SN2 plus electron transfer. This is going to be your Z. It's 2. Yes, go ahead. So this is 2. Log. And this is, I guess, the part where you could go south if you. The other part you can go south is not knowing your reaction, like equation. But you have to pick one of these numbers to put on the top and one of these numbers to put on the bottom. How do you place the numbers, the 0.3 and the 0.15? It says the oxidized form goes on the top and the reduced form goes on the bottom. Out of SN4 plus and SN2 plus, which one is the oxidized form? 4 plus, the one with the more positive charge, right? Remember, oxidation more positive. Oxidation more positive. So that means we're going to put the 0.3 on the top and the 0.15 on the bottom. So far following me? Then you have to plug this in your calculator. 0.15 plus 0.059 divided by 2 log of 0.3, what? And you should get a very small difference. I got 0.15. 0.159. 0.159. And you do need to write the significant figures, a minimum of 2, meaning you either need to write it as 0.16 or 0.159. So 0.16 by changing the concentrations. How exciting. That's why I said it only works to positively flip spontaneity if the difference is within 0.3, because the differences will be rather small, depending on how much the concentrations are changed. Because really what you're doing here is taking the log of 2. That's what you're doing. All right, so far so good? So this is my non-standard E cell for tin. This is E cell for SN4 plus to SN2 plus at these new concentrations, right? So now we're going to move forward, and the question is going to ask us, what is the E cell under these conditions? Can we figure that out? We know that the SN4 plus to SN2 plus is positive 0.16 volts. What was the other part of the half cell? It said it was made of tin, and the other one was aluminum. And we need the data booklet for this number, because it's an older question. So we need to figure out, well, what is the standard E cell of aluminum, because we've got standard concentration. So go back to aluminum in your, keep this, in your data booklet. I'm going to go find aluminum, because again, I have not memorized these, so I'm really telling you don't memorize all these numbers. If I have not memorized them, definitely don't memorize them. Negative 1.66, right? So negative 1.66. So we know that aluminum plus 3 to aluminum is negative 1.66. Now what do we have to do to figure out the E cell? This is a 6, right? This is the same number from here, the 0.16. 0.16, the 0.159, or the 0.16 that we calculated, right? This should be 0.16. Now, how do we calculate the E cell? We've got 2 half cells. How do we know it's oxidized? How do we know it's reduced? We have to analyze the numbers. The more positive one is the reduction here for your E values. The more positive one's your reduction, and the more negative one is your oxidation. Yes? So then it's E red minus E ox is the E cell, which is positive 0.16 minus negative 1.66, positive 0.16 plus 1.66, which gives you 1.8, welcome back, 1.82. Are we good with this? This right here was from the last question. Here, that was that one. Yes? Okay, overall cell reaction. So now we've got SN4 plus 2E minus goes to SN2 plus. And with the aluminum half cell, because that's an oxidation, we would do what with the tap reaction? Swap it. So it's aluminum goes to aluminum plus 3 E minus. Now what do we do? So first it's obtain the half reaction, flip the oxidation. So it's obtain half reaction. Flip the oxidation. That's what you saw me just do. And now what? Combine the half reaction. But can I combine them right now? No. Why not? In order to combine them, the amount of electrons transferred must be the same. Amount of electrons transferred must equal. And if they don't, what were we supposed to do? This is 2 electrons and this is 3 electrons. What are we supposed to do to make them the same? The first number that 2 and 3 go into, which is 6. So multiply the first equation by 3 and the second equation by 2. So it's basically multiplied by whatever number will make the electrons the same and distribute by that number. So this would become 3SN. This would become 3SN4 plus 6E minus. Do you really have to write this? Or could you just go straight to the answer here? You could. You don't have to prove this. This is enough information. But just in case you accidentally don't distribute everything, it's important to recognize these cancel, right? And then everything else combines together. So my final answer here would be 3SN4 plus 2 aluminum goes to 3SN2 plus 2Al plus 3. And that's it. So they've given you space here to combine the reactions, right? That's what they're giving you the space for, is to recognize how to combine those 2 reactions. How many marks is this worth altogether? 2, 3, 4, 5, 6. So, and if you put the half cell 4 marks there, like to actually make the diagram, you're talking these questions run somewhere between 10 and 15 marks, actually, on a paper 4. One of the things about paper 4, I think I've mentioned it, but I'll say it again once a unit, is unlike AS chemistry, where some things show and some things don't show, in this class, every unit shows. You will have questions on electrochemistry. You will have questions on thermal stability. You will have questions on enthalpy. You will have questions on acids and bases. Like, you'll have every topic in this, because there's less topics. Every topic will show. So here you're looking somewhere between 10 and 15 marks for these types of questions. And they're pretty predictable, like what they're going to be. So that's kind of good news. You can more prepare. for what that paper 4 is going to be on. But it's also bad news because everything's going to show. So if you're bad at a topic, that topic will be there. So as usual, you should play your strengths and get all the marks you know you're good at first, and then go back to the ones you know you're not so great at. Because part of it's going to be time. 2 hours for 100 marks is tight. You will not probably be able to finish that exam in 2 hours, to be fair. So you go to all the points you can get, which means find the easiest for you first. We'll talk more about exam strategies when we get closer to the time, but I can tell you that the best thing to do is look at each question, look at the topic, and be like, yeah, I like that one. Let's do that. Or, yike, let's go to the next question. Here we go. This is the last standard, actually, for the day. I told you that this lesson is not too crazy. You should have actually time to work on homework today, I hope. Should we get through these last sections? We're on slide 13 out of 17, so we should be done before 9 a.m. You should have some time to work on the homework, which I'll talk about. The relationship between cell forces and the standard Gibbs free energy is this equation, and this one should also be memorized. I hope they add in actually more with delta G in this class. I hope in the 2028 syllabus change, which doesn't affect you at all, that they do add more, because actually there's a bunch of relationships you can make. This one you do not need to memorize. But is a way to relate the equilibrium constant and the item gas law into delta G, actually. So this equation is the one we're going to focus on. Delta G equals negative NFE. Equilibrium constant. Like Ka, Kd, Kc, all of those. So it's a way you could relate gases into spontaneity of reactions. But anyway, relationship between electric potential and delta G is here. And there's something really important here. Let's review something real quick from Unit 2. What's delta G? Oh, by the way, I'm giving you back your exam today, your quarterly. What's delta G? There's a question on the quarterly that literally said, what is the name of delta G? Gibbs free energy.
I got that wrong.
Delta G is Gibbs free. It was the title of the lesson. Energy. Which means, is there energy available for that reaction to occur or not? And you were supposed to memorize the signs at which a reaction was spontaneous or non-spontaneous. So if delta G was negative, and I think some of the better scored points were calculating for delta G and delta S. A lot of students did pretty well on calculating for delta G and delta S. But if delta G was negative, this would tell us the reaction was spontaneous. Do you remember that? Well, write it down because it's not going away. And if delta G was positive, that meant it's non-spontaneous. And what did we just say about E values? When E is positive, it's spontaneous. And when E is negative, it's non-spontaneous. So this is the equation that relates the two together. When delta, you can see that here, because when delta G is positive, this is negative. So they're opposites of each other. This equation proves that to you. That the E cell will always be the opposite side to delta G. So what does this equation say? N is going to be moles of electrons transferred again. So N is moles of electrons transferred. If you want to put Z, you can. Don't ask me why they use these. Because N is actually used a lot for moles. Actually, the question is, why don't they use N for moles here? Right? That's the question. Because N is usually used for moles. If you think of PV equals nRT, N is moles. So why? Neither here nor there. F stands for something we learned earlier this unit, which is called the Faraday. And so the one thing I want to point out about the Faraday here is it's 96,500 coulomb per mole of electron. But there's other units it can be described as. It can be described as joules per mole over volt. This is important. Why is this important? Delta G was supposed to be in what unit? I think, do you remember what delta G is always supposed to be in? Kj mole minus 1. This equation is going to give you delta G in what unit? Joules. Which means just like before, you're going to have to change joules to kilojoules by moving your decimal over 3 spots. So joules will always have to be changed to kJs. I mean, it'd be easier if you just did, instead of writing 96,500, you could do 96.5 and then kilojoules, but whatever. That's the equation as stands. And then E cell, well, that's going to be your standard cell potential. So this is the standard overall cell potential. And so this is an Olympiad note. I'm going to recruit, if people want to do it, some students who want to do the Olympiad for chemistry. It's in March. So if you're interested in that, I'm going to bring that up at the Science National Honor Society meeting this month. You don't have to do it, but it's something that could go on your resume. It's basically a chemistry competition. If you do well enough in it, you qualify for nationals. I have had a student qualify for nationals a couple years ago, and they get a fancy dinner, and they get to sit with all the chemists in South Florida, and they give out awards and stuff. So you're among the elite chemists of the area, and they present their research. So it's pretty cool. But that's coming up. I haven't really talked about it much yet because my goal for all of you is, to pass your Cambridge exam. But if you're really interested in potentially being competitive in chemistry on a national level, that is a competition that I do sponsor. It's called the Olympiad. The initial round of it takes place in March, and it's just a multiple choice test, actually, the initial round. After the multiple choice test, if you qualify for nationals, then you actually do a lab as part of the national competition. Yeah, it's interesting. You want you have to qualify.
Dinner is what's up.
The dinner. Last year, what I had the students do is those students who wanted to compete that were part of A-level were actually just able to do it within class time. We just took because it's only a 2-hour exam, so we just took one class period and did it. And yeah, but those who didn't want to do it didn't have to. So we'll talk about that more at the SNHS meeting, how we're going to construct that this year. It just depends on where the student interest lies. But I do sponsor that specific competition for the school. Usually to qualify for nationals is somewhere around 35 out of 60. It's not an easy test. It's everything in chemistry. All right, so practice question. I'm going to go over a few questions here. There's not a lot of reference questions on this specific equation because it's new for 2022. And so the delta G equals negative NFV equation doesn't really have that many practice questions to go off of. But I pulled this one off of my old college textbook. And so what you're going to see here is the writing here is a little bit different. And this is how in America that cell potential is actually provided to you. What they do is they say this is one half cell and this is the other half cell. And this right here represents the salt bridge. And what they do is they actually tell you what's happening. You read it left to right. Calcium goes to calcium 2+, and silver plus goes to silver. So they tell you what's being oxidized, and they tell you what's being reduced. This is being oxidized, and this is being reduced. This is the anode, and this is the cathode. This is how, when I was learning it, how it was presented in America. So it's always anode to cathode. And then it would always be left to right if written in this way, the electron flow. So they first ask you to write the balanced redox reaction between these two and calculate the standard cell potential using standard reduction potential. So given in this way, I think it's actually easier to write the balanced redox reaction because they're telling you what's being oxidized and they're telling you what's being reduced in what order. So we know calcium goes to calcium 2+, where would the electrons be? Left or right side? You have to include the electrons in your equation. Where would they be? If it's being oxidized, electrons are on the right. Does anybody know that? The idea being 2 plus and 2 minus would cancel and become 0. The electrons have to be on the right-hand side. The charges have to be balanced. And then for silver, where would the electrons be? From silver to silver. Silver plus 1 is 0, silver 0. Where would the electrons be, the left or the right? If this is the anode, the electrons are being released. If this is the cathode, the electrons are being accepted going in. So where are the electrons in the second equation? On the left-hand side, right? And then plus 1 minus 1 makes 0. The charges are balanced. Now, how do we balance these two reactions with each other? Multiply the bottom one by 2. That's it. This will allow the electrons to cancel, which we have to. And then what would our final reaction be? Ca plus 2Ag plus goes to Ca2 plus 2Ag. What would the reduction potential be? How would we figure that out? Standard reduction potentials, where do those come from? If we don't have them, they come from the data booklet. So for calcium and for silver, we need to get their numbers from the data booklet. So for calcium, what's it going to be?
Negative.
Calcium negative 2.87 and silver is positive 0.80. So we know calcium is negative 2.87 and silver is positive 0.80. How do I put those numbers together? What's the way to do it? How do we calculate the E cell? E red minus E ox. Which of these is the reduced one? They're telling you. They tell you it's the reduced one is the cathode, is the silver, right? But also the number, the more positive number is the one that's reduced. This one is oxidized, so it's going to be 0.80 minus negative 2.87. And so when you put those two numbers together, you get, I get 3.67 volts. Now, part B is where we actually have to use this formula. It says, using the standard cell potential obtained in part A, what will the Gibbs free energy be? So what would delta G be? Negative N F E. What is Rn? 2. 2 electrons were transferred, right? 2 electrons were transferred in this process. One lost 2, the other one gained 2. So N is 2. Faraday is a constant that's given to you on the Cambridge exam, 96,500, right? And then E was something you found in the last question, the 3.67. And yes, this answer will be in joules, right? So when I multiply these three numbers together, I get some crazy large number. I get negative 708,000. Check to see if you get the same thing, because I was solving this yesterday. Joules per mole. But we don't write that as a final answer, do we? What do we write? Move the decimal over 1, 2, 3 spots, and it's negative 708. I would just do 3 significant figures and call it kilojoules per mole minus 1 would be my final answer here. Check to see if that's what you got. 3.67. Not 367 volts, there's nothing. My goodness. Think about a 9-volt battery. 367 volts, that would be putting a lot of energy through you. I have to think about those fences. Have you ever seen those fences that they like hold like farm animals in that have electricity flowing through them? I wonder how many volts those are. Can anybody search that up? How many volts are those fences? Because I was thinking like, that'd be a lot of volts. I've touched it accidentally before and it's like a shock that goes through your whole body. Yeah, when I was a kid, we would like try to go under the fence to like get into my friend's yard. It was their own farm. It was my friend's farm. So we would jump the fence, and then I accidentally touched it one time. I was like, oh, that's a bad idea. Okay, that's a lot of volts. If you have a heart condition, it can starve your heart. What? Those little fences. With those, I don't know if you guys have ever like seen a farm where they have those electric fences that keep the animals out.
For $1. Yeah. I need like 50
to do that. I did it for free, accidentally. Wasn't intentional. That's how you learn things. Apparently, I didn't have a heart condition because I survived.
No, I don't have a heart condition, so I'm fine either.
But it does give you like a pretty big shock through your system.
Okay, 200.
Anyways, so the electricity you'll be working with on Thursday is nothing like that. You'll be working with like these volts, like 3 volts, 4 volts, a 9-volt battery. It will not put that much energy through you if you accidentally were to, you know. All right, try this one. See if you can try it. The process that I just went over, it's another question. See if you can try it. Remember, you can use the data booklet. You'll want it. Well, actually, you don't need it because they gave you this. They gave you 2 half reactions. They're asking you for the overall reaction, put the two together, and the standard cell potential. And then they want the delta G. So see if you can try this one. You've got to figure out what's being oxidized. You've got to figure out what's being reduced. If you get it right, I'll get you a stamp. So I've already solved all of this. I spent yesterday solving these, and I solved all your homework questions too. Very exciting. You want to go home with it? You get to go home tonight. Yeah, good. Yeah, good. I'll be right back with the stamp. You didn't. That'd be like 3 marks. You got like 3 or 4 marks there. It's not a Cambridge paper 4 question, but it would be like 3 or 4 marks if it was. Delta G. Yeah, I think so. Just gotta know which one to subtract.
You have to put the overall reaction.
Yep. Were you able to figure out which one's reduced and which one's oxidized?
This one's the.
Beautiful. We're almost done. This is the last standard. More positive one is the reduced one.
Yeah.
This is reduced. This one's oxidized.
Over nothing.
All right, waiting to see. You need that brain break? Or are we, for example? Always. Always flip the oxidation because you have to put the electrons on the other side. Because they have to cancel by one being on the reactant side and the other electrons being on the product side. So, and then you have to make sure that the electrons are the same, right? So you have to multiply 2 by the first number 2 and 5 go into. So multiply 1 by 5 and 1 by 2. How did you get a negative number?
You're supposed to get negative numbers.
You are supposed to get a negative number for delta G.
Oh.
For part B. You're not dumb. Nobody here is dumb. Wow.
We're not entirely dumb, but sometimes we make dumb mistakes.
Anybody can make a dumb mistake. And there's different kinds of smart too. There's street academics.
Yeah, I have no smarts.
There's mechanically smart. There's not smart.
I do that all the time.
If somebody tells you don't look, that's really what people do is they look. Because like I tell them
But some
with the
people
white,
are
bright white
subtle.
light with the magnesium, I'm like, don't look at it directly. Let me tell you how many people look at it directly.
There was like,
You're not supposed to.
It's like
You're gonna have a spot in your eye.
You told me
It was worth like 20 minutes, I was
so now I'm
Now you
inclined
have to do
to
it.
look at it now.
Yeah, but I gotta cover my bases. It's like safety wise, do not look at that.
for A?
Yeah.
1.636.
Okay, yes.
Is this correct?
I do not have. So I'll tell you what the issue is. You're close, but it's not right. There's one mistake, but it's only, well, you would get 1 out of 2 marks because it's one mistake.
It's not good enough.
Not good enough.
Which one? Which half? Like.
All right, I'm gonna give the answer for example 2. For the equation, if you got 2 MnO4 minus plus 16H plus 5 Pb in whatever order, and then on the other side 5 Pb2 plus 2 Mn2 plus 8 waters, that's probably worth 2 marks. The other part, which is the new thing, should have been negative 10, right? Because there were 10 electrons transferred, 96,500, and then this would be the cell potential. The overall cell potential here would have been 1.51 plus 0.126, which is 1.636, which is what goes here. And then that gives me some crazy large number, like negative 1.5 million. But that's, when you see a crazy large number for delta G, what should that communicate to you? It's in joules. So just for yourself, if you don't remember, just think about it. Oh my gosh, that's like in the millions or the hundreds of thousands. That means it's got to be in joules. But you want it to be in kilojoules. So you move this over, and it's negative 1,578. Okay, that sounds more normal. So then in joules, this would be the answer.
Oh.
And in kilojoules, this would be the answer. Joules would be that. Kilojoules would be that. So be careful with that. For that one, they said they wanted in joules. So then it would be this one. Yes. Yes. As long as the amount of significant figures are the same, so it would have to be at least 2 decimal places, I believe. So it'd have to be 1.64. I think you rounded it 1 spot too many, because the traditional rules for sig figs, this is 3, this is 2, so you should have 2 decimal places in your answer. All right, next example is actually from a Cambridge exam. So example 3 comes from a Cambridge exam, a recent one. Cell reaction for electrochemical cell in B is shown. So they give you, this is the overall reaction, right? They already gave you the E cell. They give you the full reaction, and they ask you for the delta G, and this time it is indeed in kilojoules. So formula, delta G equals, here's where you could go wrong. How many electrons are transferred here? 2. How do we know it's 2? If we break up any of these half cells 2Fe2 plus 2Fe, or sorry, goes to 2Fe3 plus. How many electrons were transferred here? One for each iron, right? But there's two of them. So it's a trap. This is 2E minus. Same thing for the chlorine if you broke up that one. If you broke Cl2 to 2Cl minus, how many electrons are transferred here? Each chlorine gains one, but there are two chlorines. So the amount of electrons transferred are actually two. That's where the trick is in this question. So this would be minus 2 times 96,500 times 0.59. When you get all this, you get some crazy large number, negative 113,870. But you know that whenever you see that big number for delta G, that is in joules, and if they tell you to make it kilojoules, you're going to move this decimal over, and it's going to be negative 113.9.
Yeah.
Or negative 114. Specifically, I checked the markings always, and it said minimum of 3 significant figures. So negative 114 or negative 113.9 would both be okay. Yes? Are we good with this? Last slide for today's lesson. I told you we'd be finishing shortly, so you'll have some time to work on questions. I'll talk about your homework. And also, there's tutoring today, so you could totally get things done today. There's no tutoring tomorrow because there's no school tomorrow. So I did move tutoring to today for that reason. Oh, you've got speech and debate. Well, there's very little time to do things. There's very little time to do things. Tuesday is tomorrow and there's no school. So we lost Tuesday. Tuesday's gone.
And then Wednesday
For STEM. All right, here we go. Use the Nernst equation, which they give to you, which I'm saying sometimes they do give it to you. It appears from the new terminology that they are giving you the Nernst equation, but I would just memorize it just in case they don't. This is the equation, and they ask you to use the Nernst equation to calculate the electric potential for the Fe3 plus Fe2 plus half cell in this experiment. So can we do that? Can we do this? Let's see if we can. So E stands for what again? Non-standard. So when you see E without the little zero, that means non-standard. That means that's what I'm going to be solving for. E0, we have that. What is E0? What is E0? It's in the question. It's literally right there. It's 0.77 volts. You don't get the data booklet here because it's a newer question. They give it to you in the question. So newer questions, they'll give you the values in the question. Then plus 0.059 divided by Z. What is Z? Transfer of electrons. From Fe3 plus to Fe2 plus, how many electrons is that? 1. Difference of 1. Okay, here's the trap. I guess it's not too big of a trap. It's a trap though. It says Fe2 plus is 0.15. Everything else is in its standard state. So your two forms of iron here are Fe3 plus and Fe2 plus. This is 0.15. Do you agree? What is Fe3 plus? So that's the oxidized form, isn't it? And this is the reduced form. That's the trap. Because it said it's standard. So you knowing standard is 1 molarity is super important here, isn't it? Because if you don't know it's 1, you're not going to solve this. You have to know that it's going to be now log of 1 divided by 0.15. Are we good with that numbers? Number placement, okay. Then it's do the math. I get 0.819. Let me know if you get the same. That's what I solved. I checked mark schemes and everything. I got 0.819. Okay. example 3, these two questions are linked together. I feel the need to tell you right now. Example 3, these last two slides, they are linked together. I'm telling you that for the last question. Use your answer to D1 to calculate the E cell for this electrochemical cell. So remember that the standard cell was 0.59. The original iron cell was 0.77. The new one is technically 0.82, right? So it went up by 0.05 from what it was before. What does that mean happens to the overall cell? Can you figure it out? The overall cell was originally 0.59. The iron value went from 0.77 when we changed the concentration to 0.82. How does that affect the overall cell? What would you do? This is one of the half cells, right? Which half cell is this? The reduction or the oxidation? How do you know? This is the overall reaction, right? Wouldn't the overall reaction tell you what's being oxidized and what's being reduced? What's happening to iron here in this overall reaction? It's losing electrons, so it's being oxidized. So if its cell value went up by 0.05, what would happen to the overall cell? Think about the equation. The E cell reaction is the E of the reduction minus the E of the oxidation. Can you think about what would happen? Iron is up by 0.05, but is that being reduced or is that being oxidized? Iron you have right here is being oxidized, which means if this goes up by 0.05, you're actually subtracting by an additional 0.05. Does that make sense? Because like this is being oxidized. So if this changes from 0.77 to 0.82, instead of subtracting by 0.77 to get 0.59, you're now subtracting by 0.82. How would that affect this answer? This is the overall. 0.59 would change to what? This is you have to think about it. This is not an easy question because you've got to think. It would be 0.54. It would. Alex has it. Why? Because if it was originally 0.59, the overall cell, and the oxidized part went from 0.77 to 0.82, that means that you're subtracting by 0.05 more than you were before, which means your overall cell goes down by, so if the original one was 0.59, but you're subtracting by 0.05 more, that means you would be subtracting this by 0.05 more, so this is 0.54. That's how you get the answer. This one you have to like mentally work out. This again is a hard question. I considered this hard when I taught it last year. That would be the hard mark. The other marks are predictable, you would get them, but there will always be some marks that you have to think to be able to come up with it. This is the one where you have to think to be able to come up with the answer. All right, that's it for the day. So we are done with all the standards in chapter 20, which is unit 3 for us. And that means you can have a test, but it'll be next week on Thursday. So next class, you will be practicing with a lab. You'll have a full class lab that day after bell work. You'll be building 2 different types of cells that we've been working on practicing these cells. We'll be practicing them with the lab. Next week, you'll be reviewing on Tuesday, and you will be doing a test next Thursday. Yes. What? I don't know, whatever day. We have this class. Yeah, we have this class. Today is Monday. Then you have this class on Thursday. You don't have school on Monday, so you have this class on Tuesday. You don't have school on Monday because it's Veterans Day. All right, let's talk about out your classwork / homework real quick that you got the last 20 minutes you can work on. Question 1, I realized today was in your last homework. So skip question 1. Everything else is to do. So question 1's the first 2 pages. So you can skip the first 2 pages. Like the first, like front and back, I mean. And then after that, from question 2 on is the actual homework. Because you did the last homework, right? So you already did that question. So start at question 2. You don't have to do question 1. I guess I really wanted you to do that specific question, that first question, since I put it twice. It's from a newer exam, so I do want you to have done that question, but you should have done it in the last homework, so you don't need to do it again. So start at question 2. Start at question 2. Doesn't matter. That's the beginning. It has to do with it. Remember to get the data booklet values. If it's an older question, you will need to consult the data booklet to get the cell values that you have to use for the math.